Our last lesson, we went over linear functions. We're going to talk about linear inequalities today uh, as well. And linear inequalities, they share a lot of commonalities with linear functions, except we're not just talking about one line on the graph. Instead, we're talking about one line on the graph um, as well as a larger shaded region on the graph. So when we say that y is less than something or greater than something, we shade a region on the graph as well as plot a linear function uh, that's related to the inequality. So we're going to look at how we can graph this in standard form, in slope intercept form, and then some of the rules of inequalities as well. So first of all, what is a linear inequality? A linear inequality is very similar to a linear equation in that there's no x squared or y squared terms with a linear inequality. We just have x terms and we just have y terms. So this example is not a linear inequality because we have an x squared term. So 2x plus 3y is less than or equal to 7. This would be considered a linear inequality. We can also solve this for what 1y would be. So we can subtract 2x on both sides. We get 3y is less than or equal to negative 2x plus 7. And then we can divide by 3 on both sides. We get y is less than or equal to negative 2/3 x plus 7 over 3. And so we would graph this line just almost the same way as we would graph it if it was an equal sign. Now I'm just going to do a rough sketch of what that would look like. So let's say that's 7 over 3. We're going to go down 2 over 3 for our slope. And again, you can graph this on Desmos, but I just want to show you what the graphing software is doing when we're graphing this. So negative 2/3 x means we're going down 2 over 3. That's our slope. And this is less than or equal to, y is less than or equal to this function. Because it can be equal to the function, that's our line. And that would be like if y equaled negative 2/3 x plus 7/3. So y can equal that. So that's part of our answer. But the second part of our answer is y is less than all of this function, less than all of this line. So we're going to shade everything below the line that is less than the line. And sometimes OneNote does this. And we'll try that one more time here. Sometimes OneNote will delete everything that I write or parts of it. So everything that's less than the line is where we would shade. So that's kind of an overview, and we'll look at some more of these on Desmos as well in just a bit. So in order to determine if something is a solution to an inequality, we can plug in these numbers. So going back to, let me zoom out here, going back to this rough sketch example of our graph, all of this that I've shaded in is the solution. And if I shade it a little bit more, that might make a little more sense. It's everything on this side of the line. So all of these points, if there's a point here or here, any point that's over on this side of the line is considered a solution to the inequality. Now, instead of just graphing and checking on the graph to see if a certain point is a solution, we can directly plug in that point or that value into our inequality. So if we want to find if 1, 1 is in that shaded region, all we have to do is plug in 1 for x and 1 for y. And we can do that here. We can do 2 times 1 plus 3 times 1 is less than or equal to 7. And we get 2 plus 3 is 5 is less than or equal to 7. And that's a true statement. So because that's a true statement, we say that 1, 1 is a solution. And if we check the rest of these doing the same method, 2, 2, we can check that's x, that's y. We're going to plug in 2 for x, 2 for y. We get 2 times 2 plus 3 times 2 is less than or equal to 7. And so now this is 4 plus 6 is 10. And this says 10 is less than or equal to 7. This is not true. So this is not a solution. I like to put big X's next to these or check marks. That kind of helps me save some time. Or you can write T or F. That can save you a little bit of time. The next one it wants us to check is -4, 5. And technically I should be labeling these just so we don't get things mixed up. So this is X3, this is Y3. This is our point number 3 here. So X is -4, Y is 5. So we're going to plug in -4 for X and 5 for Y. And we get 2 times -4 plus 3 times 5 is less than or equal to 7. 7 is less than or equal to 7. This is also a true statement. It can be equal. 7 can be equal to 7. And so it is a solution. So 4, 5, -4, 5 is a solution. All right, so we talked a little bit about how to graph these linear inequalities. You just graph the line like it's an equal sign. Then you put in the inequality symbol, whichever of the 4 that it is. If it can be equal to it, we write a solid line for our line that we're drawing. It's just a regular line, like how we would graph a regular line. If it can't be equal, if it's just greater than or just less than, our line is not a solid line. We draw a dotted line instead. And then we pick a point randomly to determine what side to shade. Now, normally if y is less than, we shade underneath. If it's less than or equal to. If y is greater than or equal to, we shade above the dotted line. So those are the rules for the general rules, but we can also pick a test point or pick a point to decide what side that we shade this on. Let's look at another example here. So let's say we have this inequality 4x plus 6y is less than or equal to 24. It says they already did step 1 and 2 for us. It graphed it, it changed it so it was just what y equaled. So it did -4x, -4x, 6y is less than or equal to -4x plus 24, and y is less than or equal to -4 over 6x plus 4, y is less than or equal to -2/3 x plus 4. And we can check to make sure that they did this graph right. So this is 4. We're going down 2 over 3, down 2 over 3. So that's how we would graph the first part of the line. It's a solid line because it's less than or equal to. All right, so now the next part is we have to figure out, are we shading above or below the line? Let me actually go back here. So this was our final answer. We have y is less than or equal to. That means we should be shading below the line. But let's say we weren't sure. Let's say maybe you forget that rule, or sometimes there might be an exception. So we can always pick a test point and see if it makes the equation true. Kind of like we did with those first 3 points there, we can pick a test point. So you can pick any point you want. I know I've mentioned in previous lessons not to use 1, 1, or not to use 1, 0, or 2 a lot of times when we're plugging in numbers. But in this case, you can use 0, 0 to test. So if you use 0, 0, that means y is 0, x is 0. We're going to plug in 0 for y, get -2/3, 0 for x, and we get 0 is less than or equal to 4. That is a true statement. Because that's true, 0 is less than 4. that means we chose a point on this side of the line. And because it's true on this side of the line, that means everything is true on that side of the line. And OneNote keeps erasing that, but we would shade all of that portion there. And that's what that looks like graphically if you did that on Desmos. And they picked 0, 0 on this example as well. Same thing here. The line y equals 3 over 2x minus 5, and then it says shade the solution set for the inequality where y is greater than 3 over 2x minus 5. So most likely it's going to be above here, but we can check with a test point, and 0, 0 is on there. And so we can check 0, 0 again. Plug in 0 for y, 0 for x, so you get 0 is greater than negative 5, and that is a true statement. Anything that's 0 or higher is greater than a negative all the time. So 0, 0 is going to be shaded on our graph. Standard form is just, standard form is basically, these are some rules for standard form. I think that it's probably better for you to just realize to solve for what 1y is, and then you can figure out the x-intercept and the y-intercept. So if you solve for, even if you don't solve for what 1y is, you can plug in 0 for y to get the x-intercept. So the x-intercept is going to be x, comma, 0. Something x for the x value and 0 for the y. The y-intercept is going to be 0 on the x and some value for what y is. That's all this is saying. This is just a shortcut if you want to memorize these. I really think it's easier if you just solve for what 1y is if we have something in standard form. And I showed you guys how to do that in the last example there. So here it says determine the intercepts of the line for 2x minus 5y is less than 20. This was the method they did. I would just suggest solving for y. So you'd get negative 5y minus 2x on both sides is less than negative 2x plus 20. We're going to divide by negative 5. And we get y is, now this is greater than negative 2 over negative 5 because we divide by negative, we switch that sign. And this is plus 20 over negative 5. Y is greater than, that's x there, 2/5 x minus 4. So we're starting at minus 4. We're going up to over 5, up to over 5. And this is a dotted line. It wants to know what the intercepts are. So here's our first intercept. And all we have to do, again, to find the y-intercept is we plug in 0 for x. So when we plug in 0 for x, we get negative 4. When we plug in 0 for y, we get 10. And so the intercepts are going to be on where the dotted line is. So we use when it's equal to it. All right, and this last one says graph the inequality. You can just graph these on Desmos. So here's how to do that on Desmos. 3x minus 4y is less than negative 24. And you could just press shift comma to do less than, or you can go to the keyboard and there's less than symbols with greater than, less than on there as well. And so it'll just tell you there's the y-intercept, 0, 6, and there's the x-intercept, negative 8, 0. So if you're doing the SAT test, you get to use this calculator. It's probably the fastest way to find the y-intercept and the x-intercept. And then all the shaded region, it shows us the shaded region here as well. All right, so I believe that's all of the examples. There's just a couple more examples on the slides here. Again, you can use a test point. You can use 0, 0. Dotted lines don't have an equals. Solid lines can be equal to, so less than or equal to or greater than or equal to.